So in the last lecture, we start with distributed source coding. In this model, we have a source which emits two sequences, xn and yn. And we have two not connected encoders, encoder 1 and encoder 2, who have to compress these sequences. They send the index of the sequence, W1 and W2, to decoder, who receive both sequences. And depending on these two indices, W1 and W2, have to make an estimate about the first sequence, xn, and about the second sequence, yn. We assume that the rate here of this encoder is R1, so we have 2 to the n to the R1 indices. And here the rate is R2, so we have 2 to the n R2 indices. And now the problem is to find a set of rate pairs for which one can, for sufficiently large n, design encoder and decoder so that the error probability PE, which is that the estimates equals not equal the emitted sequences, can be made an arbitrarily small positive number. So we want that this error probability goes to 0 if n goes to infinity. You can see already that this problem is very similar to the source coding problem which we have in the beginning. There we saw, if you have one, there we had one source which emits one sequence to one encoder. This was sent to the decoder, and here you have to make an estimate. And there we saw that he can compress the sequence until h of x, where x is the random variable of the random variable x. That means if these two encoders can communicate as much as they want, then we of course can apply our method, and then we can get the entropy of xy, the joint random variables. But these encoders don't work together. But you will see that Slipyam and Wolf showed that also then we can achieve this. So here you see the result. The result is that we can get the following rate region. That we can achieve rate pairs R1 and R2 in such a way that R1 is greater or equal h of x conditional on y, that R2 is greater or equal h of y conditional on x, and that R1 plus R2 is greater or equal the entropy of the joint distribution xy. And this was a surprise when Slipyam and Wolf get this. And the new idea we got here is binning. So we not only construct codes of rate R1 and R2, we also have this R1 prime and R1 2 prime here. And this somehow is the number of code words we construct per indice. So normally in our methods before, we only prepare one code word for one index, but here we prepare a code book with several code words for one index. And we use 2 to the n R1 prime or 2 to the n R2 prime number of code words per index. So in totally, we generate 2 to the n R1 plus R1 prime code words for xn. So we have W1, which goes for the indices. It goes from 1 until 2 to the n R1. And V1 is in principle for the variance of each code word. The same is for x2 there. And the idea is, again, that we generate this code book randomly, like we did in the theorem before. So we use a distribution px just to generate this code word for the encoder 1 and we use the random variable py to get the codebook for the encoder 2. Now for the encoders, so the encoder share, of course, their codebooks with the receiver or decoder. And to encode encoder 1, he receives the sequence xn from the source, and then he tries to find w1 tilde and v1 tilde in his codebook such that it equals the emitted sequence. And if there is one or more such pair, then the encoder 1 chooses one by a predefined function. So we only need these predefined functions if there is more than one variant of the codebook. So otherwise, we can also choose a function in such a way that we always choose the first one in the list. If unsuccessful, then encoder 1 chooses W1 and V1, 1, 1, and send this to the decoder. And encoder 2 do the same with his code word. Now the decoder, he receives two indices, W1 from encoder 1 and W2 from encoder 2. Then he looks at the two code books he has and chooses V1 and V2 in such a way that xn of W1 and V1 tilde and yn of W2 and V2 tilde is jointly typical. If something like this exists, then he put out the corresponding sequences. If unsuccessful, he put out just the first one. So he put out xn W1 1 and yn W2 2 1. Just to see this idea in more detail, so for each bin, so this is called a bin. So this is for index 1 for encoder 1. So you have a whole bin of code words for index 1. You have a whole bin of code words for index 2. And you have a whole bin of code words for index 2 to the n R1. So here you have all bins, and the same is done for encoder 2. And now the decoder, he knows this code book and he knows this code book here, and then he looks if he can find for the indices some point in such a way that these code words are jointly typical. So in this way, that xn w1 v1 tilde and yn w2 v2 tilde is in the set of typical sequences. And this works. So we showed with this method that we can achieve this rate region. That was the last thing we did last lecture. So what we did, we consider again error events, and we look at when do these error events go to 0. So we want to have, of course, that this total error event PE here, that this total error event goes to 0. And we showed that we have such condition that it goes to 0, that we can achieve this rate region here. What we now want to do is to show that this rate region is also optimal. So we will show the converse.